All right, so we're going to go over an example. And we're going to use this very similar example for the dependent and the independent t-test to kind of indicate the difference between the two. So here we're looking at is arachnophobia, otherwise known as the fear of spiders, specific to real spiders, or is a picture enough? So we took, for the dependent t-test, 12 spider-phobic individuals. So these 12 individuals were exposed to a real spider, and they were also exposed to a picture of a spider, of that very same spider. Now, obviously there's issues with this test. We can call it being confounded. If you showed everybody the real spider first and then everybody the picture of the spider second, your data would not be exactly random. So in this case, what you have to do is you have to alternate. Half the group would have to see the real spider first, and half the group would have to see the picture first. Therefore, we can reduce the confounding and the error associated, or the learned behavior associated with this dependent t-test. So half the group will look at the real spider first, half the group will look at the picture first. And anxiety will be the outcome. That's what's going to be measured. You want to go ahead at this point and run the SPSS example so you can kind of see how we do all the different t-tests. You can do that now, or you can just go ahead and continue. All right, so here is the output for the dependent t-test. It's going to tell us the average anxiety that's associated with looking at the picture versus looking at the real spider. We did have 12 people that looked at each. And again, it shows our standard deviation and the standard error of the mean. That standard error of the mean is simply the standard deviation divided by the square root of the sample size. So that is how that is calculated. So no craziness there. No, I didn't have to write it. How about that? All right, paired sample correlations. So this is really telling us our correlation. So we're going to check this just to make sure of a few things. We're going to compare the anxiety and look at this correlation. 0.545 is a pretty large correlation, right? But it is not significant. And when we do the dependent t-test, this correlation piece will be very important to look at because we do want to have some consistency in the results because we have same participants, but we would like some heterogeneity as well. So we don't want there to be a correlation. This is kind of getting a little bit concerning if our level of confidence is a p-value of 0.05. It's not significant, but we're kind of closing in on the potential for it to be significant. It's not, so we'll just kind of put that aside for now, and we'll go ahead and look at the output for the paired samples t-test. All right, the mean. This piece here is the mean difference of the two conditions. And you'll remember the picture of the spider had an anxiety of 40, and the real spider had an anxiety of 47. So 40 minus 47 gives us a -7. The t-value is equal to that -7 divided by our standard deviation, 9.807, which gives us our -2.473. And we have degrees of freedom is equal to n-1, so 12 minus 1 gives us 11. So what SPSS is doing is it is looking up in those statistical tables for you, and then it is telling you whether or not it is significant. And it is significant. So we do have a significant difference in anxiety. All right, let's double check to make sure our analysis is still going to hold up. Something that we want to verify is to make sure that the confidence intervals do not contain 0, and the confidence intervals do not contain 0. So the true value of the mean is unlikely to be 0, which is exactly good. So we don't want mean 1 minus mean 2 to equal 0, because that would mean that they're exactly the same. Right? So if we take mu1 minus mu2, let that equal to 0, that essentially means that mu1 is equal to mu2. And if we're trying to find out whether the picture of the spider is different than the real spider, if you thought that they were, then you would want this outcome. If you don't think that they are, then you do not want that outcome. So here we do not have that outcome. Now that 0.031, we'll go to understand a little bit more what this means, what the significant difference really is. So in truth, there's only a 3.1% chance So there's only a 3.1% chance that the t-value could actually happen if the null was true. So that means that there is a significant difference. So we know that mu1 cannot equal mu2. So we know that mu1 does not equal mu2. Our t is negative, which just means that the first condition had a smaller mean than the second. And that's going to be important. So the first mean actually had a smaller mean than the second. Well, if that first mean is the picture and the second mean is the real, we can say one thing for absolute positive. So the exposure to a real spider, because mu2 was greater, caused significantly more reported anxiety than a picture of the exposure at a 95% level of confidence. So now not only do we know that there is a significant difference in the anxiety, we know that we had more anxiety with the real spider than with the picture, as we would have hoped. So that is absolutely critical. This is where I talked to some of you about regression and correlation is a lot of gray. There's absolutely no gray here. It is black and white. We know for a fact that the real spider caused more anxiety than the picture of the spider, and we can go ahead and move on from there as to what you want to do with your research. So this is really why I like the t-test, the ANOVA. We get a black and white answer. Was there a difference? Yes, there was. Real spider was worse. Now, if you had an idea, because the default value right here is always a two-tailed. So if you want a one-tailed, you're going to have to divide that two-tailed significance by 2. Again, you would only run a one-tailed if you had an idea that one would be greater than the other. All right, the last thing that we need to check when we run a t-test is to look at the effect size. So unfortunately, SPSS does not calculate this for us, so we have to calculate it ourselves. But we can simply use the data. This is all the data that's provided in that table. So we end up with an R value of 0.6. These R values are very exactly like we talked about previously. So here we do have a large effect. Now, these correlation and these effect size start to take a different meaning at this point. And this is where engineers, it should really matter to us. So the real spider caused more anxiety than the picture of the spider was statistically significant. But because we have a large effect size, it also means that there's a practical significant difference. A good example of how this would not work, let's say we're checking speeds along our roadway. And that mean difference of speeds along the roadway was 0.5 miles an hour. Well, if we had such a large sample size, we could actually find a statistically significant difference in the half a mile an hour. But if anyone has driven, you look at your speedometer, there's no way you can really tell the difference between 62.5 and 62 miles an hour, let alone between 62 and 63 sometimes. So it's really not practically significant, and this is where we would hope that our effect size would tell us, well, yeah, it's statistically significant, but if it's not practically significant, should we even implement it? Probably not. So we always want to look at the effect size because that's going to tell us the practicality of the statistical test we just ran. Now, with the dependent t-test, we have one problem. If we have correlation between the variables, that R value may be overestimated. So we had some pretty large correlation. It wasn't significant, but this is something that we might want to say, well, it could be impacted because of some pretty strong correlation. But that's the only gray area we have associated with this type of a test. All right, let's go ahead and move on to the independent t-test. Sometimes this is called the student's t-test. The null hypothesis is very similar to what we had before. mu1 is equal to mu2. Mu minus mu2 is equal to 0. We have two conditions that we have to meet with the independent t-test. We have to find out whether or not our variances are homogeneous or heterogeneous. And depending upon whether they fall into which category will impact the equations that you would use or that the SPSS will be using to figure this out. So if you have homogeneous variances, these are the equations that SPSS will use. If you have heterogeneous variances, we're going to change up the equation just ever so slightly. But again, you don't need to know those equations. Just wanted to let you know why there was a difference. And then the t-test itself, the mean of 1x minus the mean of 2x minus, and this value is 0, divided by the standard deviation. Now, degrees of freedom gets a little bit crazy. If you have unequal sample sizes, because we have to have those different n values thrown in there with the standard deviations. But again, no need to worry. Sometimes that's why you'll see funky degrees of freedom in the independent t-test, is because they're going to have to use this equation with unequal samples. All right, let's use that same example, arachnophobia. Here, because it's independent, we're going to have different people looking at the picture of the spider and different people looking at the actual spider. So here we've got 12 people looking at the reel, 12 people looking at the spider, the picture of the spider, and still measuring anxiety. So if you want to look at the SPSS t-test, independent t-test, again, it's a good time to take a break and do that, or we can go ahead and look at the output. All right, these statistics are just telling us what everything looked like. So we've got means, standard deviations, and standard of errors. And then the first test we want to look at for the independent t-test is the Levene's test. Levene's test is for homogeneous variances, as it says. So it is running an f-test, and we have the significance. So this significance is what we want to look at for whether or not we have equal variances. So it says it's not significant so therefore we can assume that our variances are equal. So what we have to do, because we're making that assumption, is we're only going to read this information. If that significance value is less than 0.05, we would read this row, but we're not going to be reading this row. This row turns out to be useless information to us. So we're not going to be looking at that. So when we look at that top row, we find out our mean difference is -7. And here's our significance right here. Our significance is greater than 0.05, which means there's no significant difference in the anxiety. Anxiety. So spider phobes, this is the outcome of the test. We can say spider phobes are made equally anxious by pictures of spiders as they are by the real thing. At a 95% level of confidence. So that is our final outcome. The effect size is calculated in the same way. So we end up with an effect size of 0.34, which is somewhat of a medium effect. So it says even though the test was not significant, there is some practical difference. So sometimes the outcome of the test is simply due to the number of data points that you had in your sample. So we had 24 data points. If we had 20, or if we have a ton more, we had a little bit of a practical difference. We might end up with a statistical difference. But at this time, with the data we have, we do not have a significant difference. And that's pretty much all we can say. Now, this all works really well if we have normal data. If we do not have normal data, we're going to have to run a non-parametric t-test. So go ahead and load up the non-parametric lecture, and we can continue on and finish up with the comparison of two.